Welcome to Understand the Math. In this Calculus 1 video, we're learning how to apply derivatives to real-world rates of change in the natural and social sciences. We'll start with physics examples involving motion, and then look at applications in chemistry, biology, and economics. Be sure to download the free guided notes to follow along and work through the examples with me. We're going to start by looking at two physics examples that involve the motion of an object. We are going to be looking at the position of an object, the velocity of an object, which is the derivative of the position function, and then the acceleration, which is the derivative of the velocity function, or you can think of it as the second derivative of the position function. Let's walk through an example that involves the motion of a particle. This can be a pretty hard problem, but we're going to go through it step by step to make sure you totally understand it. We're told that a particle moves along a straight line according to the law of motion. S of t is equal to t cubed minus 9t squared plus 15t plus 10, where t is time and it is greater than 0. And it is measured in seconds, and our position function s is measured in meters. We're going to begin by finding the velocity at time t. Let's go ahead and let's write down what the position function is. We're given that right above. S is t cubed minus 9t squared plus 15t plus 10. The velocity is the derivative of the position function. So we're just going to take the derivative with respect to t, and this gives us 3t squared minus 18t plus 15. And that's what the velocity is equal to. Let's look at the next part. We are asked to find when is the particle at rest. Whenever the particle is at rest, the velocity of the particle is going to be equal to 0. So we have to find t when the velocity is equal to 0. We're going to take our velocity function that we just found, 3t squared minus 18t plus 15, and we're going to set that equal to 0. Let's pull out a 3 and see what we have. We have t squared minus 6t plus 5 is equal to 0. We can factor that. This gives us 3 times t minus 1 times t minus 5, and that's equal to 0. This means we're going to set t minus 1 equal to 0, and we're going to get t is equal to 1 second. And then we're going to set t minus 5 equal to 0, and we're going to get t is equal to 5 seconds. So our particle is at rest at 1 second and at 5 seconds. Let's now look at part C. We want to find when is the particle moving in the positive or negative direction. A particle is moving in the positive direction when its velocity is greater than 0, and then it's moving in the negative direction when its velocity is less than 0. So what we're going to have to do is find when the velocity is positive and when the velocity is negative. I'm going to start by writing down our velocity function in the factored form. We just found this. It's 3t minus 1 times t minus 5. And we know that our velocity is equal to 0 when t is equal to 1 and when t is equal to 5. So what we're going to do is we're going to look to the left and the right of 1 and 5 to see what the velocity is equal to. Let's go ahead and let's draw a number line. This is our time, and we're going to put in that time starts at 0, and then we have 1, and then up here we have 5. It's okay if it's not drawn to scale. I'm going to put on here that at 1, our velocity is 0, And at 5, our velocity is also 0. We have to look in this region, and this region, and see if our velocity is positive or negative. I'm going to create a table over here. I'm going to put down t, and then I'm going to put down t minus 1, t minus 5, and then our velocity function. So what I'm going to do is I'm going to pick a point in each interval and then see if t minus 1 and t minus 5 are positive or negative, and then we can tell what is going on with the velocity. Between 0 and 1, I'm going to pick the point 1/2. So 1/2 minus 1 is negative, and then 1/2 minus 5 is negative. So when we multiply two negatives, we're going to get a positive because our velocity is t minus 1 times t minus 5 times 3. Now I'm going to pick a point between 1 and 5. I'll just choose 2. 2 minus 1 is positive, 2 minus 5 is negative, so our velocity is negative. And then lastly, I'm going to pick a point that is greater than 5. So let's just say 6. 6 minus 1 is positive, 6 minus 5 is positive, so our velocity is positive. So I'm going to add in our table here that our velocity is greater than 0. In the middle region, it's less than 0. And then in our region on the right, it is greater than 0. We can conclude then that our particle is going to be moving in the positive direction when our velocity is greater than 0, and that happens in our first region when t is between 0 and 1, and then in our region on the right when t is greater than 5, and then our particle is going to be moving in the negative direction in our middle region, and that is when t is between 1 and 5. It's moving in the positive direction for these values of t and the negative direction for those values of t. In part D, we are going to draw a diagram to illustrate the motion of the particle. Since it's talking about the motion of the particle, I am going to go ahead and write down our position function. S is t cubed minus 9t squared plus 15t plus 10. To illustrate the motion of the particle, we want to find our position function s when t is equal to 0 and v is equal to 0. That will be our mean position points, and then we'll fill in between. Let's first look when t is equal to 0. All we have to do is look at our equation for s and substitute in that t is equal to 0, and we get that s is equal to 10. Let's now look when our velocity is equal to 0. We actually already found this. This is going to happen when t is equal to 1 and when t is equal to 5. When t is equal to 1, our position function is 1 minus 9 plus 15 plus 10, just plugging in for t. And this gives us 17, and we need to put units on this. Our position is in terms of meters, so I'm going to write down 17 meters. When t is 5, s is going to be 5 cubed minus 9 times 5 squared plus 15 times 5 plus 10. And when you add all of that up, you end up with a value of minus 15 meters. Now we're going to go ahead and start our diagram. The time values that we're interested in are t is 0, t is 1, and t is 5. And then the position values are 10, and I just realized I did not put meters there, so I'm going to put in meters. And then we have 17 and minus 15. Since this diagram illustrates the motion of our particle, we're going to have a number line here, and this is going to be in terms of our position s. The position numbers I highlighted in orange, so we need to put in minus 15, we need to put in 10. This is not really going to be to scale. And then 17. When t is 0, our position is 10 meters. So I'm going to put a dot here, and I'm going to mark this t as 0. When t is 1, we are at 17 meters. So I'm going to put a dot here and put in t as 1. And then when t is 5, our position is minus 15. Now we can go ahead and draw the motion of our particle. It's going to go along this way, and then it's going to curve along the other way until we get to 5, and then it's going to change directions again. So we'll put some arrows on here, and you can see the motion of our particle. In part E, we are going to find the total distance traveled during the first 8 seconds. We are going to use the graph that we just drew for part D to help us answer this. We are going to have to divide our distance into 3 parts. This first part, where our velocity is positive, and then this second part, where our velocity is negative, and then the third part, where our velocity is positive again. So we're going to write down that our distance is equal to the absolute value of s at 1 minus s at 0. And then we're going to have the distance for the portion that I outlined up here in purple. That is going to be s at 5 minus s at 1. And then our second blue piece, which is going to be s at 8 minus s at 5. Let's go ahead and see what this is. Let me pull this back down so we can see these numbers. S at 1, we calculated up top, and it was 17. So this is 17. S of 0 was 10. And then S at 5 was minus 15. And we're going to subtract off S at 1, which was 17. And then we're going to get to the part that we don't know yet, and that is S of 8. Let me go ahead and highlight this. That one we actually haven't calculated yet, so let's go ahead and let's do that. S at 8 is going to be 8 cubed minus 9 times 8 squared plus 15 times 8 plus 10. And that ends up being equal to 66. So now we can go back up and plug in that S of 8 is 66. And then we subtract off S at 5, which was a minus 15. So you have to watch your negatives here. Let's come down here and see what we have. This is going to be 7 plus the absolute value of minus 32, which is just 32. And then we have 66 plus 15, which is 81. And this adds up to be 120, and we need to put units. It is in terms of meters. So the total distance traveled in the first 8 seconds is 120 meters. Now let's look at part F. We want to find the acceleration at time t. The acceleration is the derivative of the velocity. So let's start by writing down our velocity function. V is equal to 3t squared minus 18t plus 15. Our acceleration A is v prime, and that is 6t minus 18. So there's our acceleration. Now we have one last part, and it is challenging, but I'll show you exactly what to do. We need to find when the particle is speeding up or slowing down. Our particle is going to be speeding up when our acceleration and velocity have the same sign. So let's write down A and V have the same sign. And then it is going to be slowing down when A and V have opposite signs. To solve this problem, we need to focus in on when the velocity is 0 and when the acceleration is 0, and then look at the intervals on either side of those points. We already looked when the velocity was equal to 0. That happened when t is equal to 1 and t is equal to 5. Now we can find when our acceleration is equal to 0. We just take our acceleration function 6t minus 18, set it equal to 0, and this gives us that t is equal to 3. So we are going to draw a number line, and we're going to put the points 0, 1, 3, and 5 on it. We're going to start at 0, and then we have 1. It doesn't matter the scale. We have 3, and then we have 5. In one of our previous problems, we saw that our velocity was greater than 0 in this region, and it was less than 0 between 1 and 5. And then when t is greater than 5, our velocity was greater than 0. Now we're going to do the same thing for the acceleration. Our acceleration is going to change signs when t is equal to 3. If we look at 6t minus 18 and pick a value less than 3, let's just say 1, we're going to see that our acceleration is negative. So I'm going to write down that a is less than 0 here and less than 0 here. And then if we pick a point that is greater than 3, say 4, you can see that our acceleration is positive. So we'll write down a is greater than 0 and a is greater than 0. Now let's look and see when it's speeding up. The particle is going to be speeding up when the acceleration and velocity have the same sign. That happens in this region and in this region. So we know the particle is going to be speeding up when t is between 1 and 3. And then when t is greater than 5. And it's going to be slowing down in this region and in this region. So that is when t is greater than or equal to 0 but less than 1, and then when t is between 3 and 5. So this is when our particle is speeding up, and this is when our particle is slowing down. We're now going to walk through an example involving the motion of a projectile. The height in meters of a projectile shot vertically upward from a point 1.5 meters above the ground with an initial velocity of 19.6 meters per second is given by the function h of t is 1.5 plus 19.6t minus 4.9t squared after t seconds. I graphed our function h of t over here on the right just so that you can see what's happening. The projectile starts 1.5 meters above the ground. That's right here. It goes up, and then it comes back down and hits the ground. We want to find the velocity after 1 second and then after 3 seconds. The velocity is the derivative of position, and our position is given by h of t. So let's write down that h is equal to 1.5 plus 19.6t minus 4.9t squared. Our velocity then is just the derivative, h prime, and that is 19.6 minus 4.9 times 2 times t. So this is just 19.6 minus 9.8 t. I'm going to go ahead and highlight that because we're going to need that again. Now all we have to do is find the velocity at 1 second and at 3 seconds. The velocity at 1 second is going to be substituting in when t is 1. So this is 19.6 minus 9.8, and that is 9.8, and velocity is in terms of meters per second. Now we're going to find the velocity after 3 seconds. So we're just going to plug in 3 for t. So this is 19.6 minus 9.8 times 3. And this ends up being a value of minus 9.8 meters per second. Notice that the velocity after 1 second is positive and the velocity after 3 seconds is negative. So that means that at 1 second, our projectile is still going up, but at 3 seconds, our projectile is on the way back down. This leads into part B, where we are going to find when does the projectile reach its maximum height. And whenever you have the word when, that means you're going to be solving for t. Our projectile is going to reach a maximum height when the velocity is 0. If we look over here on our graph, it's going to be at this point right here where the slope is equal to 0 because the slope is the derivative and the derivative is the velocity. So we need to find t when our velocity is equal to 0. Our velocity function was highlighted up here in yellow, and it's 19.6 minus 9.8 t, and we're going to set that equal to 0. So we have 19.6 is 9.8 t. If we divide by 9.8, we get that t is equal to 2 seconds. At 2 seconds, our projectile is at its maximum height. Part C is a kind of a follow-up from that. Part C is asking us, what is the maximum height? The maximum height is going to occur at 2 seconds. So we need to find h when t is equal to 2. Let's go ahead and write our function for h. It is 1.5 plus 19.6t minus 4.9 t squared. And now what we're going to do is we're going to let t be equal to 2. So this gives us 1.5 plus 19.6 times 2 minus 4.9 times 2 squared. If you plug all that into your calculator, you end up with 21.1, and that is in terms of meters. This means that the maximum height of the projectile is 21.1 meters. Let's look at the next question. This question asks us, when does the projectile hit the ground? When our projectile hits the ground, our position is going to be 0. So we want to find t when our h is equal to 0. So our h is 1.5 plus 19.6 t minus 4.9 t squared, and we're going to set that equal to 0. We are going to have to use the quadratic formula to solve for this. And you can think of the quadratic as at squared plus bt plus c is equal to 0. So t is equal to minus b, so that's minus 19.6, plus or minus the square root of b squared. So we have 19.6 squared minus 4 times a, which is 1.5, times c, which is minus 4.9. You have to be a little careful with the negatives. And we're going to divide all of this by 2 times a, which is 1.5. If you put that into your calculator, you end up with two values. T is minus 0.08 seconds, and then 4.08 seconds. We know that time cannot be negative, so we're going to put an X through that solution. And that tells us that the projectile is going to hit the ground at 4.08 seconds. We have one more question. The question is, with what velocity does it hit the ground? So we want to find the velocity at the time when it hits the ground, and that time is 4.08 seconds. So we want to find V when T is equal to 4.08 seconds. Our velocity function was 19.6 minus 9.8 t. So all we have to do is substitute in that t is 4.08. So this gives us 19.6 minus 9.8 times 4.08. If you put that into your calculator, you end up with a value of minus 20.38 meters per second. It makes sense that our answer is negative because our projectile is traveling in the downward direction when it hits the ground. Let's now walk through an example involving a chemical reaction rate. We're going to consider a chemical reaction where the concentration of a reactant decreases over time. The concentration at time t is given by the function c of t is 0.05 times e to the minus 0.1 t, and c is measured in moles per liter, and t is measured in minutes. We want to find the rate at which the concentration is changing at t equals 10 minutes. The rate at which the concentration is changing is the rate of change of the concentration with respect to time. So that's just the derivative. So we are going to take the derivative with respect to time of our function 0.05 e to the minus 0.1 t. Because we're going to have to take the derivative of an exponential, let's just remind ourselves that the derivative with respect to t of e to the at is just a times e to the at. You just bring the constant that multiplies your t out in front. dc dt is then 0.05 times minus 0.01 e to the minus 0.1 t. If we multiply this out, this gives us minus 0.005 e to the minus 0.1 t. We want to find the rate at which the concentration is changing when t is equal to 10 minutes. So we are going to calculate dc dt when t is equal to 10. So we're just going to substitute in that t is 10. So this is minus 0.005 e to the minus 0.1 times 10. So this is just minus 0.005 times e to the minus 1. If you put that in your calculator, you get a value of minus 0.001839. And now we have to think about units. Our concentration is in moles per liter. And then our time, which is the variable in the denominator because it's dc dt, is minutes. So our units are moles per liters times minutes. And this then is the rate our concentration is changing at 10 minutes. Let's now walk through a biology example involving logistic growth. The population of a bacterial colony is modeled by P of t is equal to 5,000 divided by 1 plus 9 e to the minus 0.6 t. And P of T is the number of bacteria, and T is measured in terms of hours. We want to determine the rate at which the population is growing when T is equal to 4 hours. The rate at which a population is growing is just the rate of change of the population, and that is equal to dP dt. So we want to find dP dt when T is equal to 4 hours. I'm going to write down our function for P, and I'm going to rewrite it just to make it easier to take the derivative. I'm going to pull the denominator up into the numerator and make it a -1 exponent. So this is 5,000, 1 plus 9 e to the minus 0.6t, all raised to the -1. Now we can find our derivative. dP dt is 5,000 times -1 times 1 plus 9 e to the minus 0.6t, all raised to the -2. And now we have to find the derivative of what's inside. And that derivative is 9 times minus 0.6 e to the minus 0.6t. Let's rewrite this, and let's take this term to the denominator. We're also going to combine some constants. I'm going to combine the 5,000, the -1, the 9, and the minus 0.6. The negatives cancel, and the constants multiply to be 27,000. And then we have e to the minus 0.6t. And in our denominator, we have 1 plus 9 e to the minus 0.6t. And that quantity is squared. We now found the rate at which the population is growing. Now we have to find that rate when T is equal to 4 hours. So all we have to do is we have to plug in that T is equal to 4. This is 27,000 e to the minus 0.6 times 4, all divided by 1 plus 9 e to the minus 0.6 times 4, and that gets squared. Now you have to put that into your calculator very carefully, and you end up with an answer of 742, and now we need units. Let's see. It's the rate of change of the population over time. So population is bacteria, so this is bacteria. And then our time is measured in hours, so it's bacteria per hour. And that's our final answer. We're going to now walk through an example that arises in economics, and it's on marginal cost. We are told that the cost in dollars of producing X items is given by the cost function C of X is equal to 5,000 plus 10X plus 0.01X squared. We're asked to find the marginal cost when 200 items are produced. Let's first talk about what marginal cost is. Marginal cost is just the rate of change of the total cost function with respect to the number of units produced. So that means marginal cost is going to be the change in cost with respect to the number of units produced. So it's going to be dC dx. And we want to find dC dx when X is equal to 200. Let's write down what our cost function is. It is 5,000 plus 10x plus 0.01x squared. Now we're going to find the derivative dC dx. is going to be 10 plus 0.01 times 2 times x, and this gives us 10 plus 0.02x. Now let's find what this value is equal to when x is 200. So dc dx, when x is 200, is equal to 10 plus 0.02 times 200. And this is equal to 10 plus 4. So we get an answer of 14, and now we need units. Cost is in terms of dollars, so this is dollars. And then our dx is in the denominator, so our x unit has to be in the denominator, and that is the number of items. So we have $14 per item. We can conclude from this that our marginal cost is $14 per item. And that's it. You've seen how derivatives can be applied to physics, chemistry, biology, and economics to measure important quantities like velocity, acceleration, reaction rate, population growth, and marginal cost. To really master these applications, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.